Let me give you a definition. Let A be an n by n matrix, and let lambda be an eigenvalue. The dimension of the eigenspace for lambda is called the geometric multiplicity of lambda. So in our last example, the first lambda here, this -3, had one vector in its eigenspace. That means its geometric multiplicity was just 1. Notice though for the 5s, we had 5 was listed twice, and we had 2 eigenvectors. The geometric multiplicity of 5 is therefore 2. Now, on the other hand, if P of lambda is the characteristic polynomial for A, and P of lambda, let's say, equals lambda minus lambda sub 0 to the k power. So I factored out that, and then I have something left over. So suppose this here is what the characteristic polynomial looks like, and lambda naught is not a 0 of the q portion. So I factored out as much lambda naught as I could, or lambda minus lambda naught as I could. In this case here, lambda naught is a 0 of multiplicity k. And I want to be careful. Multiplicity is going to be changed to, it's a 0 of algebraic multiplicity 2. So when you look at the multiplicity in here, with regards to the characteristic polynomial, if you look at the multiplicity there, that's called the algebraic multiplicity. The geometric multiplicity is the dimension of the eigenspace. Those two things will be crucial in what we're going to do. Here's a theorem that I'm going to state without proof. The reason why is it's a lengthy, sort of a lengthy thing, and it uses techniques that I'm not sure are very useful to this course. So although there are some nice insights, I'm going to avoid it nonetheless. So here's what I have. For A in M n by n, and any eigenvalue of A, let's say, and lambda, any eigenvalue of A, the geometric multiplicity of lambda is less than or equal to the algebraic multiplicity of lambda. So just remember it this way. GO mult is always less than or equal to alg mult. Geometric, size of the dimension that is spanned by the eigenspace for lambda. Algebraic is the number of times that lambda is a zero of the characteristic polynomial. So let me do an example. We did this one earlier, but I'm going to do it again, or a little bit of it again. It's easy to tell in any kind of an upper diagonal or upper triangular matrix, the eigenvalues are on the diagonal. So the eigenvalues are lambda equals 5 and 5. So 5 has algebraic multiplicity 2. Now, when we solved this before, when we did, I'll sort of remind you, we did 5 minus 5, 0, 1, 5 minus 5, 0, 0. We ended up with the following, 0, 1, 0, 0. And we had one free variable, which was x. So the eigenspace was equal to the span of the single vector 1, 0. So the geometric multiplicity of that particular lambda is 1. So we can see here it's strictly less than. So it can't actually be strictly less than, but it's always less than or equal to. Now what we're going to do is there's several theorems here that all use probably lengthy computational proofs, so I'm going to avoid them. But what they say is important. So let me go ahead and do this. So A in M n by n is diagonalizable. IFF. Remember, this means if and only if. The sum of the dimensions the eigenspaces equals n. And we've seen that for the last several of them. If in this last example, n here was 2, but we only had one eigenspace and it only added up to 1. So we didn't have enough vectors. We needed 2 linearly independent vectors. And so if we're going to have n linearly independent vectors, then these eigenspace dimensions better add up to n. Furthermore, the dimensions of the eigenspaces is n. I should probably say the sum of. So that little thing needs to be the sum of the dimensions of the eigenspaces is n, if and only if, and there's 2 criterion for that. The characteristic polynomial factors completely. Into linear factors. And the geometric multiplicity equals the algebraic multiplicity for every eigenvalue. So that's when you know you've got it, is when the dimension of the eigenspace is equal to the algebraic multiplicity for each and every eigenvector. Let me do an example. Now, most of these, I'm not going to do a hardcore big example, not just yet. I just want to illustrate some facts about what I just said here in this theorem. It's a complicated theorem, so let's go ahead and do it. Do this example. Determine whether the matrix is diagonalizable. So what is my matrix? I'm going to put 1, 1, 2 down the main diagonal. And then I'll go 4, 5, 6 for the rest. Now we already know that lambda equals 1, 1, 2 are eigenvalues. In fact, if we do the characteristic polynomial, char poly p of lambda will equal lambda minus 1. I should probably, if I were really careful about this, that actually is not that. It's going to equal 1 minus lambda squared times 2 minus lambda. That's the format it will actually come in. So what do we have? 1 has algebraic multiplicity 2. So lambda equals 1 as algebraic mult 2. And lambda equals 2 as algebraic multiplicity 1. So I need the geometric multiplicities to do that. So let's start with lambda equals 1, and let me look at a minus lambda I and find the null space of that. So I'll have 1 minus 1, 4, 1 minus 1, 0, 5, 6, 2 minus 1. And let's see what happens here. Of course, those ones all go away. I get 4, 0, 0, 5, 6, 1. Now think of this in terms of x, y, and z. Here, this last row here tells me that z equals 0. Well, if that's true, then this matrix I can rewrite as this. Since z is 0, there's no need, I shouldn't say that, I can use that 1 to wipe out. You don't actually wipe it out like this. So I can use this 1 to wipe out the entries above it. And we can see that z equals 0. I have that. But this up here says that 4y equals 0, so that y equals 0. Well, then what happens is z is 0. The only free variable I have is 1. So x is the only free variable. That means the eigenspace for lambda equals 1 is, it's actually the span of this, not just this vector. So the geometric is 1. Since GEO mult does not equal alg mult, the matrix is not diagonalizable. Next example, determine if the matrix is diagonalizable. Here we have first column 1, 0, 0, 0, the next one 0, 1, 0, 0, 1, 4, 9, 0, negative 1, negative 2, 0, 9. So now we have 4 eigenvalues, but we have lambda equals 1, 1, 9, 9 are eigenvalues. Each one of them has algebraic multiplicity too. So lambda equals 1, 1 has algebraic multiplicity of 2. And lambda equals 9, 9 has algebraic multiplicity 2 as well. So first let's find these eigenvectors and see what's going to happen. So start with lambda equals 1, and let me go ahead and subtract it from the diagonals. And oh, don't forget, we want to set this equal to zeros here. We are trying to find the null space of a matrix. We say 0, 0, 0, 0, 0, 0, 0, 0, and then I'll get 1, 4, 8, 0, and I'll get negative 1, negative 2, 0, 8. This last line here says z is equal to 0. And the second to last line actually says, well, you know what, I should be careful, or x, y, z, w. All right, so let's use those letters instead. So it says, the second to last line says z is equal to w, z is equal to 0. And the last line says w is equal to 0. So what I can do is use this 8 to clean out stuff above it, and then I can use this 8 to clean up stuff above it. So what we'll end up with when all is said and done is the following. So when I use row 2 to clean out the items above it, I will have the following. And then I'll use row, well, that was row 3 to clean out above it. Then I'll use row 4, this 8, to clean out everything above it, so I can eventually get to this. I have x and y are free. And z and w both equal 0. So my eigenspace for lambda equals 1, 1 is the span. And since x and y can really be anything, x, I can let 1, 0, 0, 0 be the spanning vectors for the x, and then let 0, 1, 0, 0 be the spanning vectors for the y. So good. The geometric multiplicity of 1 is the same as the algebraic multiplicity of 1. So this has GO mult 2, same as the algebraic multiplicity of before. Now let me continue and do the same thing. Let me have my matrix back. So let me go ahead and copy that thing down. All right, let me take this out. Let me take this out. This time I'm going to subtract 9s from the diagonals. So subtract 9, subtract 9, subtract 9, subtract 9. That was my second eigenvalue. And here's what we get. Negative 8, 0, 0, 0, 0, negative 8, 0, 0. 1, 4, negative, well, actually 1, 4, 0, 0. And then negative 1, negative 2, 0, 0. This is far more complicated than the previous one. If you see, I can't clean this up any. I can, if I try to divide the first row by negative 8 or something like that, I'll get fractions. If I try to add or subtract or anything of these, I'm going to get stuff I don't like. So let me just write these down there. I get negative 8x plus 1z minus 1w equals 0. And then I'll get negative 8y plus 4z minus 2w equals 0. So let me solve for x and y. So in the first equation, negative 8x plus z minus w equals 0, I'll get negative 8x equals negative z plus w, and then x can equal negative 1/8 negative z plus w. On the other hand, for the second one, I have negative 8y plus 4z minus 2w equals 0. I'm going to divide that equation by negative 2. And so that'll give me 4y minus 2z plus w equals 0. 4y equals 2z minus w. And then I can divide by 4. So y equals 1/4 2z minus w. So z and w are free. They can be whatever they want to be. So that means I'm going to have the dimensions of this particular eigenspace will also be 2. That matches the algebraic multiplicity. Beautiful. Let's finish this off since I am pretty much almost done with it anyways. So I could start with this. I could say let z equal 8 and let w equal 0. When I do that, x will be negative 1/8 times negative 8 plus 0, and that will equal 1. Y will equal 1/4 times 2 times, what did I say, 8 minus 0, that'll be 4. So this eigenvector that I get from here, x will have been 1, y will be 4, z will be 8, w will be 0. And then I can also let's do z equals 0. That's not the part, but I want to see what will make, I think I'm going to let w equal 8 because that'll wipe out the fraction. So I'll let w equal 8. So x equals negative 1/8, 0 plus 8, that'll be negative 1. Y will equal 1/4 0 minus 8, which will be negative 2. This gives us another eigenvector. X is negative 1, y is negative 2, z was 0, but w was equal to 8. So the eigenspace for lambda equals 9, 9 is the span of those two vectors. So I have 1, 4, 8, 0, negative 1, negative 2, 0, 8. See, by the time you figure out whether it's diagonalizable, you pretty much have done the diagonalization. That's what I'm getting at. So we have the geometric multiplicity of lambda equals 9 is 2. So geometric mult equals algebraic mult for all eigenvalues. So the matrix is diagonalizable. Another way, we have 4 eigenvectors. They're going to be linearly independent. What is the breakdown then? Well, for our P that we want to use, remember, you want the eigenvalue or the eigenvectors in order. So let me do this. Let me come back here to where I got my answers first. And I'm going to call, what I'm going to do is lambda 1 will equal 1. V1 will equal that first vector in there. 1, 0, 0, 0. I don't know where else I'll put it. Lambda 2 will also equal 1, but V2 for my second eigenvector will be 0, 1, 0, 0. So you got to make sure you have them in order. Just make sure you have the eigenvalue with the associated eigenvector. These two vectors could be swapped, and it wouldn't make any difference if you swap these two vectors because they're with the same eigenvalue. Now, then what I'm going to do is this. I am going to let lambda 3 is going to equal one of the 9s, and then V3 will be 1, 4, 8, 0. And then this here will be my lambda, this will be my V4, will be the second matrix. So let's get these matrices, these vectors in order. My first vector was 1, 0, 0, 0. My second was 0, 1, 0, 0. My third one is 1, 4, 8, 0, right? 1, 4, 8, 0. And my fourth one is negative 1, negative 2, 0, 8. Pretty easy to see that that thing is invertible, isn't it? My diagonal matrix will be a 4 by 4 as well, but it will have the lambdas listed on the diagonal. If you were going to do all this multiplication, and you can, once again, this is something you can check on your calculator, 1, 0, 0, 0, 0, 1, 0. This is explicitly the diagonalization of A that I want you to see. Let me check that one. It's possible that when you did your eigenvalues, you got the negative of one of mine. No big deal. So in this case, you can really tell that this matrix here, the first one is diagonal, or not diagonal, is invertible, because you can see it's an upper triangular matrix, and the determinant is just the product of the entries on the main diagonal. As long as none of these are 0, you know you have an invertible matrix. So this is the explicit diagonalization of A. Here's another theorem. Let A be an M, n by n, have eigenvalues. Let's say lambda 1, lambda 2, up to lambda sub r. And let those, so let them have those eigenvalues. Let each lambda sub k have b sub k as its eigenspace. If A is diagonalizable, then the b sub k's taken. Well, let's put this. Then I think a better way to put this is then the union of the B sub k's is a basis for r to the n. And I think when we looked at the last example, let's take a look at what we had. In the last example, the eigenvectors notice that there's 4 linearly independent eigenvectors. So since they are linearly independent, they form a basis for our n. And the n in this case is 4. All right, so there's a lot of theory, a lot of stuff in this. I want to end with some practice examples to make sure that you can understand some of the theory that goes along with all of this stuff. What I'm going to do is I've chosen some theoretical type questions from the current textbook that we're using, and I'll write them down and we'll discuss. So I'm going to start with, let's say A is a 3 by 3 matrix, and it has 2 eigenvalues. Okay. Each eigenspace is one-dimensional. Is A diagonalizable? Well, the answer to this is no. The sum of the dimensions of the eigenspaces is 1 plus 1. I was told that I have 2 eigenvalues. Each one had 1 eigenvector. This is a total of 2. Unfortunately, that does not equal 3, which is how big they need to be. You need at least 3 of them. So the answer to this is no. Here we're going to have A is in M 7 by 7, and it has 3 eigenvalues. One eigenspace is 2-dimensional, and another eigenspace is 3-dimensional. Is it possible that A is not diagonalizable. So is that even possible for that to happen? Well, let's take a look. If the third, remember it has 3 eigenvalues, if the third eigenvalue has a one-dimensional eigenspace, then the dimensions add up to, so what do we have? We had a 2-dimensional one, then we had a 3-dimensional one, and now this one is a 1-dimensional one. That's a total of 6, which is not equal to 7. So is it possible that it's not diagonalizable? The answer to this question is yes. Here's one that may or may not. It depends on how you're doing it. If you're working, say, via a computer program or something like this, this might be a very useful result. Suppose A has n linearly independent eigenvectors. So it's diagonalizable as well, I'm saying that. Prove that the transpose of A also has n linearly independent eigenvalues. So here's how we do this. For the proof of this, we have A has n linearly independent eigenvectors. And I said, I keep doing this myself. You got to be careful. Make sure that you use vectors when you're talking about linear independence. It doesn't make sense for eigenvalues to be linearly independent. So first, A has n linearly independent eigenvectors. I'll use this notation. This is the same as if and only if A is diagonalizable. That was the first theorem in this section, I believe, that we did. So that's true if and only if A is equal to P D P inverse, where D is diagonal. Okay, now I'm just going to take the transpose of each side of this matrix, or each side of this equation. Now the way the transposes work is you get the transpose of each individual matrix, but in the reverse order. See what happened? Right here, the P inverse came first, then the D because it was in the middle, and then this P transpose. But this is the same as P transpose inverse. A diagonal matrix is the same as its transpose because the diagonal is unaffected by a transpose. Now if you look very closely, this does have the look of a diagonalized matrix. It is of the form, if you will, like this, where Q is equal to P to the T. So this is diagonal. So we have A to the transpose is diagonalizable. And that's the same as A to the T as n linearly independent eigenvectors. Here's an example. Construct a 2 by 2 matrix that is diagonalizable but not invertible. Well, this one's not as hard as you think it is. Just the really simplest example I can think of is the following. It's not going to be invertible because the determinant is equal to 0. So the determinant so it's not invertible. However, it's already a diagonal matrix. So it's diagonalizable. If you really want to see why a diagonal matrix is that way, if you really wanted to see that, we could do this. 0, 0, 1. I put the 1 in the wrong place. 0, 1. The easiest thing then is to just do the identity matrix. And the inverse of the identity matrix is the identity matrix still. But you can see then not only is it a diagonal matrix, it is equal to this breakdown that shows it's diagonalizable anyways. Diagonal matrix is automatically diagonalizable. I don't know if I stated it, but that's one of those things that should be pretty evident.